All right, here we go. This is another video that I'm expecting that my students are watching to get a better understanding of a special topic. This is a topic that often is assessed on the AP Calculus exam. The topic is functional analysis. And functional analysis, this is where we were looking at the relationships between a function, its first derivative, and the second derivative. This is where we would look at questions like this. You might say, okay, here's my graph of f of x, and based on my knowledge of the graph of f, what can you tell me about the graph of the derivative f prime? And we would look at things like, for example, over here, I see that f has a relative maximum, and at a relative maximum, at least a smooth kind of relative maximum, your tangent line has a slope of 0, and so if I was sketching f prime would have to have a root. For me, f prime is in purple. I've got another horizontal tangent line right over here, so that means another place where I have a root. What else can we say? We can say that f of x is increasing on this interval leading up to the relative max, which means that f prime, if f is increasing, f prime is positive above the x-axis, and you have to be getting closer to this root. Between your maximum and your minimum, I can see that the graph of f is decreasing. F prime would have to be negative, but I have to be negative passing through this root and this root, so my graph's going to go down for a little bit, but then it's going to come back up. And then I can see that f is increasing again, so that f prime is positive. Right? These are the kinds of conversations we were having way back when. I could also then grab a different color, and we could talk about the graph of f double prime. We would look at things such as, well, if f prime is the graph in purple and f double prime is in green, then anywhere where your first derivative has a horizontal tangent line, your second derivative has to have a root. When your first derivative is decreasing, your second derivative is going to be negative, so below the x-axis. Where your first derivative is increasing, the second derivative is positive, so above the x-axis. Now I'm drawing my graphs, my f prime, and f double prime in a very specific way, because my original graph was cubic, degree 3. I would expect then that the derivative will have one less degree, so degree 2 quadratic. And then my second derivative is 1 degree less than that, degree 1, which is linear. Now, that was just a quick recap of some of the f prime, f double prime relationships that we've studied. What I want to do is I want to fill out the summary table so that you have everything in one place. It might be a little tough to see, but this top row is everything we know about the graph of f. And then down here, we're going to talk about what we know about f prime. So for example, if f is increasing, f prime must be positive. Your derivative is positive. If f is decreasing, f prime is some negative value. When your graph has a relative maximum, the only thing you can say is that f prime is making a change from positive to negative. Now, a lot of students will make a mistake and say a relative maximum must look like this guy over here, and what they forget is that you might actually have a sharp point, a cusp point, where the graph is not differentiable. That's still a relative maximum, and that's why the only thing we can say with certainty is that f prime changes from positive to negative. Similarly, if f has a relative minimum, then f prime makes a change from negative to positive. If you have a cusp point, something like this guy here, or maybe something like that guy there, we know from the previous video that these functions fail to be differentiable at a cusp point, which means that your derivative does not exist. Those are the basics. Now let's keep going. If I have a graph that has a horizontal tangent line, let me sketch a graph over here that has a horizontal tangent line. Maybe I'm thinking of the graph of y equals e to the negative x. Well, what happens is that as your graph gets, here's my horizontal, oh, my bad. We'll come back to that for horizontal asymptote. Sorry. If your graph has a horizontal tangent line, just meaning that your tangent line is horizontal, then the derivative must be equal to 0. If your tangent line is vertical, then the derivative does not exist. If your graph has a critical point, now critical point, and this one's important, there's two different kinds of critical points. There are critical points where the derivative is equal to 0, and there's critical points where the derivative does not exist. A critical point is just a general term for either of these behaviors happening. Now let's get back to horizontal asymptote. For example, the graph of e to the negative x. I can see that as I approach infinity, my graph is decreasing. Well, what does that mean about the derivative? If I imagine drawing tangent lines, a tangent line here, a tangent line here, a tangent line here, what's true if my graph has a horizontal asymptote is that the tangent lines will start to flatten out. The derivatives will approach 0. However, if my graph has a vertical asymptote, say for example the graph of y equals 1 over x squared has a vertical asymptote at x equals 0, as your graph gets closer, closer, closer to that vertical asymptote, again drawing some tangent lines, what you'll see is that the tangent lines start off relatively flat, and then they increase in slope, and increase in slope, and increase in slope. Or, depending on how your graph behaves, they're going to decrease in slope. Either way, as you get closer to your vertical asymptote, your slope becomes, your tangent line becomes more vertical, and your slope becomes undefined. What I like to tell my students is this: if my graph of f has a vertical asymptote, then f prime also has a vertical asymptote. And it'll have a vertical asymptote at the exact same place. Now let's look at f prime and f double prime. If my graph is concave up looks like this, a cup that would hold water. If we examine the derivative at different points along this curve, what you'll see is that f prime is always increasing. Because f prime is increasing, f double prime must be positive. Let me draw down here a larger version of a graph that's concave up. If I look at the tangent lines, any tangent line that I draw to that curve will be below the graph. So below the graph, which means that if I ever decide to use my tangent line to approximate the value of the function, let's say I want to know the exact value of the function at this point, but I don't know, for whatever reason, I don't know the function or I don't have the right information, what you do is you look at the point on the tangent line that has the same x coordinate, and what you'll see is that that point must be below the graph. Therefore, what you're getting is an underestimate. And we'll talk more about this in a little bit. However, if you were to connect 2 points with a secant line will intersect your graph in 2 or more places. Those secant lines, if I'm looking inside the graph, those are always going to be above the graph. And if I were to use the secant line to approximate the value of the function at a given x value, the secant line will always give you an overestimate if your graph is concave up. Now, similarly, for concave down, we could sketch a graph that is concave down. We could look at the derivatives. We could draw in our tangent lines. There's one, there's one, there's one. You can see that those the tangent lines will always be above the graph, meaning that you're going to get an overestimate. Sorry, I skipped these 2 boxes. We'll come back in a second. If, however, I use a secant line to connect 2 points on the curve, inside the curve, if I'm using the secant line to estimate, I can see that the secant line is below the graph. And if the secant line is below the graph, then it absolutely must be true that your approximations are going to be an underestimate. Now, what I missed awkwardly If the graph is concave down, f prime must be decreasing, and your second derivative must be negative. A point of inflection is where your graph changes its concavity, maybe from concave down to concave up. There's your point of inflection. Or from concave up to concave down. There's your point of inflection. If the graph changes from concave down to concave up, or concave up to concave down, what happens is that your derivative makes a change, either from increasing to decreasing, or it's a change from decreasing to increasing. If your first derivative changes from increasing to decreasing, then your second derivative changes from positive to negative, or the changes from negative to positive. So there we are. That's the summary table. This is everything that you need to know and know well for f, f prime, f double prime relationships. Now, one quick thing before we leave the summary table. We're talking about little f prime, and little f double prime. These are derivative relationships as you work your way down the chart. Don't be surprised if the College Board starts you with the antiderivative, and they start to ask you questions like, where is big F going to be concave up? Well, if big F is concave up, then its derivative, little f, is going to be increasing. And little f prime, the second derivative, would have to be positive. They might give you g, g prime, and g double prime and ask you about the relationships there. They might look at a physics question and tell you about the position function, or ask you about the position, and you need to remember that the derivative of position is velocity, and the derivative of velocity is acceleration. These are the things that you want to keep in mind as to how we're going to apply all these derivative relationships. Let's keep going. I want to look at what I would consider to be a relatively tough free response question, but I think we're going to be okay with this. Let g be a continuous function with g of 2 equal to 5. The graph of the piecewise linear function g prime, the derivative of g, is shown above on the interval -3 less than or equal to x less than or equal to 7. So I want to make a couple of things clear here. We know that g is continuous, and some of you might be thinking, of course g is continuous. I see it. No, 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 no. This is g prime. This is the derivative of g. This is that sort of sneaky thing the College Board does to make sure you're reading carefully. Find the x-coordinate for all points of inflection of the graph of y equals g of x on this interval -3 to 7, and justify your answer. When you're working with questions like this, you must make sure that your justifications go back to the graph of g prime. So I'm asking you about the graph of g, but I don't see g, I see g prime. Well, what is true? G has a point of inflection. What does that mean about g prime? G prime has to change from increasing to decreasing, or g prime makes a change from decreasing to increasing. Now, don't overthink this. What does g prime look like? We know what g prime looks like. The question is, where does g prime change from increasing to decreasing? Well, I can look at the graph, and I see that right over here at x equals 1, that's the x-coordinate where my graph stopped increasing and starts decreasing. So that's one place. Now, are there any other places where we change from increasing to decreasing? No. But there is a place where g prime changes from decreasing to increasing, and again, I want just the x value, so we're going to list x equals 4. The College Board would likely give you 1 point for both of the x values, and then 1 point for the justification, for a grand total of 2 points. Now they might decide instead to say, okay, if you get one of the points correct and have the justification, 1 point. If you get the other point correct and the justification, 2nd point. Okay. All right, part B. Find the absolute maximum of g on the interval -3 to 7. Absolute max. Now this is where things get tricky, and I probably didn't give you enough space to write. Whenever we talk about absolute maximum, what we're looking for is the largest value. And this is different from a relative maximum. Let me do a quick little sketch here. If I have a function, say, with a starting point over here, and my graph looks something like that, not arrows, but starting point and ending point, well, this guy right over here is your relative max, and this is a relative max because my graph changes from increasing to decreasing, but I can see this isn't the highest point. This is just a place where the graph stops increasing and starts to decrease, whereas the highest point is at this end point. This is your absolute max. So you got to be really careful and make sure you know what type of maximum we're talking about, relative or absolute. In this case, we want the absolute. Normally the place that we start is we look for our candidate. And the candidate is your internal candidate. We're looking at for a place like this, where the graph changes from increasing to decreasing. So where does g prime change? Where does g change from increasing to decreasing? Wherever that happens, g would have a relative max. Well, again, I don't see g in front of me, but I have g prime. I'm looking for where g prime changes from positive to negative. I look at the graph. Where does g prime change from positive to negative? Well, that happens at x equals 2, and it looks like that change happens nowhere else. That's my candidate. That alone isn't going to do it. That just gets me the candidate. I then also have to look at the endpoints. The endpoints, they said look at x equals -3 and x equals 7. What I need to determine is what is the value of g at 2, at -3, and at 7. I need all three of those values. Now you might say, wait, how am I going to figure that out? I don't have the graph of g, I have a graph of g prime. Well, if you go back and read the question carefully, they told you in the beginning that g of 2 was 5. So, okay, I know that g of 2 is 5. Did they tell me what g of -3 is? No. Did they tell me what g of 7 is? Nope. All that they've given me is 1 point on the curve, and now they're asking for other points. This is where you need the fundamental theorem of calculus. Okay, the FTC says that f of b equals f of a plus the integral from a to b of f prime of x dx. That's your fundamental theorem of calculus. If we apply the fundamental theorem of calculus here, that says that g of 7 is going to be g of 2, the point that I know, plus the integral from 2 to 7 of g prime of x dx. Well, what's g of 2? G of 2 is 5. The integral from 2 to 7, well, here's x equals 2, here's x equals 7. Remember that the integral means an area calculation. You need to find the area from x equals 2 to x equals 7. I need all of this area and that area. Fortunately, they're both triangles. This triangle is below the x-axis, so we have negative area. And the area of a triangle is going to be 1/2. The base has a length of 1, 2, 3, 4. The height is 2, going to be negative. Plus this last triangle has a base of 1 and a height of 1, so 1/2, 1 times 1. I am going to clean this up and simplify. 1/2 times 4 times 2 is 4, plus 1/2. We get 1 plus 1/2, which is 3/2. What's g of negative 3? G of negative 3 is g of 2 plus your integral from 2 to negative 3 of g prime of x dx. We know that g of 2 is 5. Now we want to be careful here. If you integrate from 2 to negative 3, you're going in the wrong direction. So we're going to do minus the integral from negative 3 to 2 of g prime of x dx. Now I'm going to admit I'm running a little low on time here. I'm going to cheat. Find the area from negative 3 to 2. So you're saying from x equals negative 3 all the way over to x equals 2. Two more triangle computations. This one has a negative area. That one has a positive area. When you're done with that calculation, what you should get is 15 over 2, which is 7.5. Okay. So the question was, what's the absolute maximum of g? Well, what are your options? 5, 7.5, and 3/2, which is 1.5. The conclusion, the absolute maximum is 15 over 2 or 7.5. And that's it. They did not ask for the x value. They wanted the absolute maximum value, and that's what we've provided to them. In terms of points, normally identifying the candidate, that's an early step in the problem, would get you 1 point. They might say something like, considering the endpoints gets you another point. Probably an area calculation, a correct area calculation somewhere in the problem is a 3rd point, and then your final answer is another point for a grand total of 4 points. And although the College Board might divvy up the points differently from time to time, that's pretty standard. 1 point for the candidate with reason, 1 point for consideration of the value of the function at the endpoints, 1 point for an area computation, 1 point for your conclusion. All right, let's keep going. Do a little folding magic here. All right. Part C. We're asked to find the average rate of change of g on the interval negative 3 to 7. Well, average rate of change, you've known that phrase for a long time. Slope. The way that we find slope, change in y over the change in x, or maybe you want to think of this f of b minus f of a over b minus a. That's great. But I want specifically the slope of g on this particular interval from negative 3 to 7, so I need g of 7 minus g of negative 3 divided by 7 minus negative 3. That's slope, this average rate of change of g. G of 7, we figured this out earlier, is 3 over 2. G of negative 3 is 15 over 2. Divided by 7 minus negative 3. Since you're on the free response part of the exam, there's really no need to simplify this, but if you want to, that's fine. 3 over 2 minus 15 over 2 is negative 12 over 2, that's negative 6. 7 minus negative 3 is 10. You want to simplify further? Great, negative 3 over 5. For this problem, they gave 1 point for the setup for your average rate of change, and then 1 point for the correct numerical value. But you could have stopped right here as soon as everything was a number and earned that first point for a grand total of 2 points. All right, last one. I need to go pick up my daughter. Find the average rate of change of g prime on the interval negative 3 to 7. Does the mean value theorem apply to the interval guaranteed a value of c on that interval such that g double prime is equal to this average rate of change? Why or why not? Oof. This one's got a lot going on. I want the average rate of change of G prime. Now, you've got some options here. Average rate of change of G prime, well, we just did that. Well, we found average rate of change of G. Average rate of change for G prime, same process, G prime of 7 minus G prime of -3 divided by 7 minus -3. G prime of 7, because I have the graph of G prime, I can find G prime of 7 to be 1. G prime of -3 is -4. Divided by 7 minus -3 is 10. You get 5/10, which is a half. That's one way you can go about doing that. There's other ways. Now, let's look at this question one more time. The second part says, does the mean value theorem applied on this interval guarantee a value of C such that G double prime of C is equal to the average rate of change? Basically, does G double prime of C equal 1/2 for some value of C on the interval -3 less than x less than 7? That's the question that's being asked here. And this is probably not a question I'd expect lots of students to get right. Does the second derivative equal to 1/2 for some value of C? Well, G prime is the function, the original function that we're talking about. We calculated the average rate of change, which is slope of secant, and we got 1/2. And I can imagine a lot of students saying, well, yeah, the mean value theorem says that if your function, if I find the slope of the secant line connecting the endpoints, so imagine I draw some function here. Here's an endpoint, here's an endpoint. If I connect those two endpoints with the secant line, that there will be a place in between where the tangent line has the same slope as the secant line. That's what the mean value theorem says. The problem, though, is this is only true if you know two things about the function. The function in question has to be continuous and differentiable. If I look at the graph of G prime is the function I'm interested in, my graph is continuous for sure, but my graph is not differentiable. Anywhere where we have a cusp point, where we don't have a smooth transition, is where we're going to have a problem. So what I would say is no, the MVT does not apply. Why? Because G prime is not differentiable. Because G prime is not differentiable, you cannot use the mean value theorem, and that's why you're not guaranteed that the second derivative has a value of 1/2. College Board awarded 1 point for coming up with the average rate of change of 1/2, and then 1 point for the answer of no with a reason, and that reason better mention differentiability. So this question's worth 2 points. And right now, I can't really see exactly how long it's been, but I know it's been about 25 minutes or so. I'm going to cut it off here. We'll continue the conversations tomorrow in class.